All right, so now we move on to our fifth unit, and it is relations and functions, and we're going to start off with lesson 1 being linear relations. So for today's lesson, what we're going to do is go through a 5-step method for both problems and identify some key terminology that we'll need going forward. So the 5-step process that we're going to use in both of our examples is we're going to create a table of values for a given situation. We're going to identify dependent and independent variables, as well as inputs and outputs. We're going to draw the graph from the table of values that we found and determine if it's discrete or continuous data. And then we're going to find an equation that matches the graph and finally use that equation to extrapolate or go beyond the context of the given problem or the data that we initially find. So right away, what we're going to do is we're going to introduce some terminology, independent versus dependent variable. This comes a lot up in science, whether it be chemistry, physics, biology, or all the math from 15 to calculus. You're going to see a lot of this revisited. Now, what do we mean by independent versus dependent variable? Let's start off with independent. Independent variables are typically associated with the variable x or on the x-axis, and we say this is our independent or it causes changes to the dependent variable. It can exist in isolation, but then once we take an independent variable, we can apply it and it will affect a dependent variable. So now we look at dependent variable, and it's typically associated with our y variable or the y-axis or our vertical axis if we want to really be specific here. And we say that the dependent variable is a result of some input variable or some independent variable affecting the outcome, which is our dependent variable. So let's look at a couple examples here. If I study for a certain amount of time, well, this is an independent variable because I can study for 5 hours, 6 hours, whatever it may be. But what is the dependent variable here? It is the score achieved on the test. Because let's say I spend 1 or 2 hours. Well, it's going to depend or it's going to affect how much I achieve on the test or how great of a mark I get. What about the number of items purchased? I walk into a store and I buy, let's say, 5 fruits. Well, depending on the amount I buy, in this case, maybe 5 fruits, it affects the total cost or the dependent variable, which is our total cost. Time traveled. I can travel across the world. Let's say I go to Croatia or somewhere across the world. Well, we know that's going to take a certain amount of time, which is an independent variable. And what is our dependent variable? The distance traveled. Distance traveled depends on the time traveled. All right, let's introduce some more key terminology here. What if we look at discrete versus continuous data? Well, discrete data is unconnected and the values in between those points do not exist in the context of the problem. Continuous data is the opposite. It says all values between points have meaning and make sense to the connection of the problem, or we can connect all the dots here. So let's look at some examples of discrete data versus continuous data. Discrete, number of items, 1, 2, 3, 4, 5, 6, whatever it may be. Number of people, I won't have 3/8 of a person. I'm going to have 1, 2, 3, however many people in whole numbers. Test scores or game score, these are very direct values. You're never going to have like a flowing game score. What you're going to have is that you're going to have a definitive test or game score. Shoe size, very similarly, we have 11, 12, and we have the half sizes, but do we have 11.1 or 13.2? No, definitely not. We only have these fixed intervals of 11, 11 and a half, 12, and vice versa, or on and on and on. Now, continuous data, we could look at this and we would say time, it's continuous because I can break apart any given time interval infinitesimally. So what I could do is say, consider if I have 0 seconds and I'm ranging this to 1 second. Well, between these two values, I actually have an infinite amount of time. And that seems very hard to conceptualize, but what we could do is break this down infinitesimally. I could break the 0 seconds into 0.0000001 seconds, and then I could go 0.0000001 second, and I could just keep making this number have any given digits I want, infinitesimally breaking this value apart. Continuous data is going to be on and on with no break. Temperature, it can fluctuate, but there's a continuation. We can have things like 7.124 degrees Celsius, and it can continue. We get this structural continuation where there's no breaks. Height and length, very similarly, it's a flowing variable. Weight and volume, very similarly there. It's continuous because we can get very infinitesimally small fractional amounts between the data points. Now let's look at some examples here. Suppose we look at the first example where we deal with the relationship between number of toothpicks and marshmallows in any given diagram where we're going to make cubes out of these toothpicks and marshmallows. So we look at the first diagram and we would realize, okay, how many marshmallows do I have? Well, if I count them up, I have 1, 2, 3, 4, 5, 6, 7, 8. So right below, I'm going to put 8 marshmallows or 8M. I then go on to my next diagram and I realize when I have 2 cubes, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 marshmallows. So I'm going to put 12 below. Now, using predictive modeling, what I could realize is that when I went from 1 to 2 cubes, what did I realize happened with the marshmallows? They increased by 4. So if I was to do predictive modeling for 3 cubes and 4 cubes, I would most likely expect to see 16 marshmallows for 3 cubes and 20 marshmallows for 4 cubes. And that goes by the idea that it's increasing by 4 or 4 marshmallows per extra cube added. Now, what's the pattern that we need to draw this diagram? If we look at our first cube, it had 2 along each column. Then we go to 2 cubes and it had 3 along each column. So in our third diagram, what we're going to have is 4 along the top. 1, 2, 3, and 4. 1, 2, 3, and 4. 1, 2, 3, 4. 1, 2, 3, 4. Now that may seem like random dots here, but we're going to connect them all to make our cubes here. So these are vertical, vertical, vertical. We have our line along the back. Now, this isn't the prettiest of diagrams, but it definitely does the trick to show what connection points are actually occurring here. There we go. There is our diagram with the cubes, and I have a couple more lines there. There we go. So definitely not the prettiest of diagrams, but what we realize is we have our 3 cubes, 1, 2, and 3, and we would count up that we have 16 marshmallows. And an easy way to do this is to, if each column has 4 marshmallows, and I have 5 columns, 1, 2, 3, and the one on the back 4, that's going to be 4 times 4, which is 16. Okay, now we go into our last diagram. Remember, when we went from our second to our third to now our fourth diagram, we're increasing the number of marshmallows in each column by 1. So now it's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then 1, 2, 3, 4, 5. Now, remember, these seem like just a bunch of unconnected points, but what we're going to do is try and draw a cube to our best of our ability. And if this isn't the prettiest of diagrams, no worries. We just need to be able to count these here. So we draw our line across here. I'm going to go back 2. We draw our line here, here. There we go. Our lines on the back, lines in the front. And there we go. We have our 4 cubes. 1, 2, 3, 4. Now, I don't expect you to be some type of crazy artist, but you should be able to at least identify that we have 4 squares. And then on top of that, when we look at this, and I need a couple more lines to finish off this diagram, there we go, we should realize that I have 1, 2, 3, 4, 5 marshmallows in each row. And if I go along, I should realize I have this row, the one in the back, and then the one through all the dots. That's 4 times 5, which is equal to 20. So we get 20 marshmallows for a 4-cube diagram of toothpicks and marshmallows. Now, what I want to do actually is we've done for 1 cube, 2 cube, 3 cube, 4 cube. What if we have instead 0 cubes? What would this look like? Well, to have 0 cubes, the number of marshmallows we would have would actually be 4, and here's why. 1, 2, 3, 4, with toothpicks in between these. What do I realize? I've drawn a 2-dimensional square. And when I have a 2-dimensional square, this is definitely not a cube, but we can still represent something or a diagram in terms of toothpicks and marshmallows, and we would say this has 4 marshmallows. Now, this is a really critical thing to bring forward in the problem because it actually is a missing data point that we need in order to complete our graph to get our equation. So please make sure that you have this component here. All right, let's continue forward here. So now that we've come up with the pattern and we've established whatever pattern's coming here, we're going to make our table of values. So in our table of values, when we had 1 cube, we had 4 marshmallows. Or I should say, we had 8 marshmallows. When we had 2 cubes, we had 12 marshmallows, and then 16 marshmallows, and then 20 for 4. We could continue this pattern for 5 cubes and 6 cubes. We just extend each a number of marshmallows by an additional 4. And then finally, this is where I wanted you to bring forward that diagram. When we had 0 cubes, we had 4 marshmallows because it was a 2-dimensional square. Now, let's plot all these points here. So we have 0, we have 28 up here, we had 5 and 6 down here. Now we need to label really accurately which one is our independent and our dependent variable. Our independent variable is always going to be our x value. So we're going to say our independent is the x and our dependent is the y. And this will always be the case here. Now, when we go to label our axes here, when I label the axes, I should have y, which is symbolic of the number of marshmallows. And then I should have my x-axis, which is symbolic of the number of cubes. Awesome. Now we got to plot our points here. So when we plot these points, we have 1 and 8. We had 0 and 4, which was from our bottom one here, or when we had 0 cubes. We then have 2 and 12, 3 and 16, 4 and 20, 5 and 24, and finally 6 and 28. Now, they say in our part 3 here, we're going to represent these as ordered pairs, or more specifically, x and y. An ordered pair is an xy solution where x always comes first, so we're going to do that actually on the graph. If you would like to do it in this section below here, that's totally fine, but I'm going to do it on the graph. We have 0 and 4, we have 1 and 8, and I'm going to erase this just to make it a little more neat. We have 1 and 8, we have 2 and 12, we have 3 and 16, 4 and 20, we have up here 5 and 24, and finally we have 6 and 28. Okay, so we put the ordered pairs for each of them as an x and y pairing, representing the coordinate on each of these. Now we want to determine the following for this situation. What is our input values? Well, the input values are always our independent variable, or the number of cubes. So we're going to go here and say it represents the number of cubes. What is the output values? The output values are always determined by our dependent variable, or the number of marshmallows. So number of marshmallows, which our short form is there. Now, our independent variable, just like we said, is directly connected to our inputs. So it is the number of cubes. Or more specifically, we can just say the independent variable is the cubes. But actually, I'm going to be a little more direct. Let's put number of cubes. We say the dependent variable, this is connected to the output, and we say this is our number of marshmallows. And maybe off to the side here, for our independent variable and our dependent, I'll just say it is our cubes, and it is our marshmallows in general. Okay. Now, is the data discrete or continuous? Remember, continuous would mean that between the data points, we have an infinitesimally small amount that we could fractionalize it into. But with this one, we should realize that the problem revolves around, I have 1 cube, 2 cube, 3 cube, 4 cube, and a certain amount of marshmallows that corresponds to each of these diagrams. I don't break these apart into fractional amounts. I don't have a quarter of a cube and say, what is the amount of marshmallows? Because we wouldn't break apart marshmallows into eighths and sixteenths and all those sorts of fractional amounts. It is a 1-to-1, meaning 1 cube has a certain amount of marshmallows, 2 cubes has a certain amount of marshmallows, and there is no data points between. So we would say that this is an example of a discrete data, or more specifically, this is discrete data. So should the dots on the graph be connected, why or why not? Definitely not. We would say no, because we have discrete data. And that's enough to say that they are not connected. Now, choose an equation that matches the graph. What strategies did you use to verify? So what we need to do is realize any linear graph is always having the form y equals mx plus b. Now, what is m? M corresponds with the slope. We know that b corresponds with the y-intercept of the graph. So in order to determine the equation, we need to not only determine slope, but y-intercept, and then we can go back and choose one of these equations. So let's actually do that on our graph here. In blue, what we're going to do is label the couple details we have. Our y-intercept, or where it crosses the y-axis, occurs right here. Our y-intercept is equal to 4, and that's representative of our b value is 4. Our slope is always represented by rise over run. Rise over run. What is that equal to in this problem? Well, let's actually draw it. I have to go up a certain amount and over a certain amount between these points. I go up 4 units over 1 unit. So this is going to be 4 over 1, which is then equal to 4, which actually maybe I'll do below here. We have an m value equal to 4. So perfect. Now we have an m value, we have a b value. Let's put these together in terms of an equation here. So I go below, and now I want to choose the option that corresponds with an m value of 4 and a b value of 4. That is actually represented by d. We have the m value of 4, we have the b value of 4. And now, why is the b value the representative of our y-intercept? Well, if x equals 0, what happens to our m? It disappears, meaning I just have the b left. So b is representative of the y-intercept. Now, let's use this equation to extend beyond the context of this problem here, or beyond the data points that we've already come up with. So they say use the equation we found just above to algebraically. So we're going to algebraically determine how many marshmallows would be needed to make a 56 cube diagram. So what we want to do is label what these variables are actually asking for. How many marshmallows? Well, when we go above, the number of marshmallows was always determined by y. It's our y variable, or our dependent variable. So we're looking for our y, which is equal to the number of marshmallows, which is equal to an unknown. And they give us 56 cubes as the descriptor. Well, the cubes, or the number of cubes, was determined by x. So the number of cubes is x, and we know this is 56. So now what we have to do is say, okay, if we're looking for y and we have the x value, in our equation, y is equal to 4x plus 4. We're going to plug in the value for x. Y is equal to 4 times 56 plus 4. And now we should get a y value equal to, and what we're going to do is we're directly going to pull up our calculator here, and I'm going to actually pull it off to the side here. So we're going to bring it off to our left, and what we're going to do is calculate this. We have 4 times 56 plus 4. This is going to be equal to 228. Now, what I want you to realize here is, what is this actually describing? It said we want to determine how many marshmallows. So for 56 cubes, we have 228 marshmallows for 56 cubes. So the nice part about these problems is we can actually steal the direct context from the question and put it back in our answer as a way to give our final answer. This is a perfectly acceptable final answer where we've not only described exactly what we found, but we use the context of the problem to assist us in this description. There is 228 marshmallows in 56 cubes. All right, now we're going to use the equation again to algebraically now determine something different. We're going to algebraically determine how many cubes could be made if we were given 460 marshmallows. How are we going to solve this? Well, we first got to identify what they're asking for. Determining how many cubes could be made. Cubes were always represented by our x variable, and this is our unknown. 460 represents the marshmallows. Marshmallows were our dependent variable, which is the number of marshmallows, and this is our part that we have as 460. So now we're going to take our original equation again. Y is equal to 4x plus 4. We're going to now plug in our y value that we know, 460, is equal to 4x plus 4. And then when we solve for x, what we need to do is we need to subtract 4 across, subtract 4 across. We get 456 is equal to 4x. A number attached to x but through multiplication, we would have to divide it. And therefore, if we go to our calculator here, if we take 456 and divide it by 4, 456 divided by 4, we should get a value of 114. Now, according to the context of the problem, what are they saying? This is the number of cubes with 460 marshmallows. So we can, again, directly steal the context of the problem here and place it in our answer as a way to make a final answer and develop it through the context. So we have an x value equal to, well, what is that x value? The number of cubes that can be made with 460 marshmallows. So don't feel bad about taking parts of the problem here and then directly putting them in your answer as a way to answer the problem, because what often happens is they give you the context that's required in order to make your answer make sense in the end. All right, let's look at another example here. We're going to look at plane altitude and a plane that's coming in, landing in Calgary. It's at an altitude of 8,000 and it decreases at a rate of 1,000 meters per minute. Let's complete the table here. So we know at time 0, it is up in the air at 8,000 meters. At 1 minute, it decreases by 1,000. So we say 8,000 minus 1,000, which will equal to 7,000 meters. And then what we want to do is fill out the rest of the table, 2, 3, 4, 5, 6, 7, and 8. Okay, at 2 minutes, it will decrease by 8,000 minus 2 times 1,000, which is equal to 6,000. And you should see the pattern continuing here. 8,000 turns to 7,000, turns to 6,000. As we take more and more minutes, or as we add more and more minutes and time goes on, each minute decreases the altitude by another 1,000. So at 3, we should be at 5,000. At 4, we should be at 4,000. At 5 minutes, we should be at 3,000. At 6 minutes, we should be at 2,000. 7 minutes, we should be at 1,000. And at 8 minutes, we should reach 0. What does that mean? The plane has landed. At 8 minutes, we reach an altitude of 0, or that it is touchdown on ground. Now, again, what we're going to do is we're going to label, if this is symbolic of our x value, it is the independent variable, the independent, and it's symbolized by the x-axis. Our y, or our altitude, is our dependent variable. And this is symbolic of our y, or our output. Now, we realize time is something that's going to be our independent variable because time goes on and on and on. And depending on the time we have, that's going to impact what our altitude is. So as time goes on, altitude decreases. Thus, we have a dependent variable of altitude because it depends on how much time passes. Okay, let's see if we can plot it all on the graph here. So our y-axis is our altitude, which is a measure of meters. We then go down to our x-axis, which is a measure of time. Now, to construct our graph, every 2 blocks, I want you to put a hash here. So we're going to go every 2 blocks. That's going to make a hash. Every 2 blocks, we're going to make a hash up here. Okay, now we're going to go and appropriately label this. So at 0 altitude and 0 time, we go 1 minute, 2 minute, 3 minute, 4 minutes, 5 minutes, 6 minutes, 7 minutes, and 8 minutes. And then we go 1,000 meters, 2,000 meters, 3,000 meters, 4,000 meters, 5,000 meters, 6,000 meters, 7,000 meters, and finally, right at the top, 8,000 meters. Okay, now what we need to do is plot these as ordered pairs. So at 0 time, we're at 8,000. So we're way up here, 0 time, 0 minutes, 8,000. We start our descent at 1 minute, we're at 7,000. 2 minutes, we're at 6,000. 3 minutes, we're at 5,000. And we would continue this pattern all the way down, filling in our graph all the way till 8 minutes when we eventually touch down. Now they say, write these as ordered pairs or as x, y points. Yet again, you could write it down in this spot here, or you can write it on the graph. I'm going to write it on the graph just to really emphasize what the ordered pairs are, but you could draw it below. So the ordered pair I have up here, 0 time 8,000. I have 1 minute, and now I'm at 7,000 meters. And I continue this pattern, 2 minutes, I'm at 6,000 meters. We have 3 minutes, and I'm at 5,000 meters. 4 minutes, and I'm at 4,000. We have 5 minutes, and I'm at 3,000. 6 minutes, and I'm at 2,000. 7 minutes, and I'm at 1,000 meters. And then finally, we touch down at this point here, which I'll draw as a squiggle below just to represent it. We're at 8 minutes and 0 altitude. Okay, we've filled in all our ordered pairs for the graph, which are symbolic of an XY ordered pair. Now, let's continue with the information below. Determine the following situation. The input values. The input values were always the independent variable. The independent variable in this case was time. So it is the time in minutes. We then say the output values was the altitude. And this was in meters. Now, what do we know? We know that the input is connected to the independent and the output is connected to the dependent. Those lines are really important to draw those parallels. So the independent variable is time. Time is continuous. It moves on and on and on. We have our dependent variable. Depending on how much time goes by, we have a certain level of altitude in meters. Now, is the data discrete or continuous? As soon as time's involved, we know the data is continuous. So should the dots be connected or separate? We know they should be connected. Yes, they should be connected because we have continuous data. There we go. Okay, now choose the equation below that matches the graph. What strategies can we use to verify? Well, to verify it, we can actually find the same thing we found before. Any linear graph is symbolic of y equals mx plus b. That's the general form for any linear graph, where we know the m is equal to our slope and the b value is equal to our y-intercept. So those are going to be some elements we need to find on our graph in order to figure out which of these equations represent our graph. Now, when we go up to our graph, because we said it's continuous, let's make sure we connect the points here. So we're going to go from the first point to the second point. And the other thing I want you to notice here is when we look at this graph, what do we notice in comparison to our last problem? Well, we have a graph that is sloping down in this problem versus if I go back to my previous problem, it was a graph that sloped up. This is going to tell us a lot about what our slope should be. So our slope is always read from left to right, meaning I'm going to go down by a certain amount of units and over by a certain amount of units between points. Each time I go down, it's by 1,000 units. How much do I go over by? 1 minute. So when we do our slope calculation, m is equal to our rise, which is negative 1,000, how much we go up or down, divided by 1. And this is equal to, in this case, negative 1,000 for m. And now what we have to do is figure out what our y-intercept is, but what we can actually see here is that our y-intercept occurs at this peak point here. Our y-intercept is equal to 8,000. And this is equal to b. So now we have a b value of 8,000, an m value of a negative 1,000. We're going to use this directly to figure out which equation makes sense. So we go below here. The only one that includes a negative 1,000 is here. Now let's explain why this is actually the correct one here, because this is our definite correct answer is B, but let's explain it. Altitude will always start at 8,000. That's our y-intercept. We're coasting at 8,000 and then we begin the descent. Descent should always be described or by this negative here. We're taking some value and we're decreasing by some other value. Now we said that it was 1,000 per minute in the air. So when we see this 8,000, which is our starting height, our starting altitude, we're in the air, and we descend by 1,000 per given minute. So that should make sense for our context of our problem here. Now, use the equation to algebraically determine when the altitude will reach 3,500 meters. Now, what we're going to do is we're going to break this apart. Algebraically determine when. So when they say when, they're talking about time, and time was our x variable. Time is equal to x, which is equal to question mark. We're looking for the time or the independent variable. We're given, in this case, 3,500 meters, and this is symbolic of our y, which is our altitude in meters, and thus this is 3,500. So we're going to take our equation, our original. Altitude is equal to 8,000 minus 1,000 t. We want to isolate for t, and we know that the altitude is 3,500. Now, when we solve for t here, we're going to start by subtracting 8,000 away. So I get minus 8,000 minus 8,000. We'll continue the problem to the right here. This means we have negative 4,500 is equal to negative 1,000, and that's t. We divide both sides by that negative 1,000 because we want to isolate for t. And therefore, we should get a t value equal to negative 4,500 over 1,000 is equal to 4.5. What is this? It is the amount of minutes, to reach 3,500 meters. Remember what we said about the last problem. You can take the information that they give you in the problem and use it as a way to answer your problem or give your problem context. What did we solve for? We determined the when, and at what point was, or what was the altitude at this specific when or this time value? It was 3,500 meters. So our answer then becomes 4.5 minutes to reach that 3,500. And that sentence gives context to the problem and tells me exactly what we're solving for. All right, last part to our lesson today. Use the equation to algebraically determine. So instead, now we want to determine the altitude. When we talk about determining the altitude, this is our y, or our dependent variable. This is the altitude, it's our question mark. What do we know in the context of this problem? They say at 5.5 minutes, which is symbolic of our time, which is our independent variable, and we know it is 5.5 minutes in this case. Okay, let's go back to our original equation here. We have altitude is equal to 8,000 minus 1,000 t. We know the time, but we do not know the altitude in this part. 8,000 minus 1,000 times the 5.5. We should realize that when we multiply that, it's 8,000 minus 5,500. And when we do this calculation, we should get an altitude of 2,500 meters. Now let's give this context. If it's 2,500 meters altitude, when is it 2,500 meters in altitude? At the 5.5 minutes. Remember, borrow the context from whatever line that you're reading this from. If they tell us we're determining altitude at the 5 minutes, then that should be involved in your answer. We get an altitude at that amount of minutes. And that would be your final answer there. All right, now it's time for your checking your understanding. Make sure you're practicing these, because that sequence of putting together your data, graphing it, and then answering questions and extending beyond, that routine is really important to practice, because it is multi-parted and it requires a lot of conceptual understanding to go with it. So please do your check your understanding.